In this animation, we'll match graphs to the math that we do in section 8b.1 of the text. There, we assume that George Exxon refines 1,000 gallons worth of gasoline every week and derives the income he needs for consuming other goods as well as gasoline from the sale of that gasoline. The price of gasoline rises from $2 to $4, and his tastes are defined by the Cobb-Douglas utility function that places weight 0.1 on gasoline and 0.9 on all other goods. George therefore has an endowment bundle of 1,000 gallons of gasoline per week, which is the horizontal intercept of his budget constraint. When the price of gasoline is $2 a gallon, he can consume as much as $2,000 worth of other goods by selling all 1,000 gallons of gasoline at $2 each. When we solve George's constrained utility maximization problem using the price per gallon of $2, his endowment bundle of 1,000 gallons, and this Cobb-Douglas utility function that places weight 0.1 on gasoline and 0.9 on all other goods, we solve for the bundle A, that's his original optimal bundle. The mathematical solution, in fact, tells us that at this optimal bundle, George will consume 100 gallons of gasoline and $1,800 worth of other goods consumption per week. When the price of gasoline increases to $4 per gallon, then George can consume as much as $4,000 worth of other goods consumption if he sells his 1,000-gallon endowment of gasoline. Of course, if he only consumes gasoline, he can still only consume 1,000 gallons. His budget therefore rotates outward through his endowment bundle to the magenta budget constraint shown. When we now again solve his constrained utility maximization problem using the new price of gasoline, we can calculate the new optimal bundle C, which turns out to be 100 gallons of gasoline and $3,600 worth of other goods consumption. Notice that we use the same constrained utility maximization problem to solve for bundles A and C. We just plug in different prices for the price of gasoline. The reason we use the same constrained utility maximization problem to solve for both of these bundles is that both of these bundles arise as actual behavior that a consumer engages in as a result of trying to do the best he can given his circumstances. When we try to solve for the substitution effect, however, we're going to ask the hypothetical question of what the minimum budget is that a consumer would require in order to reach his original indifference curve. We can plug bundle A into the utility function to find that the label on the original indifference curve is 1,348. We then set up the constrained expenditure minimization problem that says let's minimize the expenditures necessary at the new gasoline price that allows us to reach the original indifference curve with the label 1,348. When we solve that constrained minimization problem, we get bundle B, the expenditure minimizing way to reach the original indifference curve at the new price. To be more precise, the math tells us that bundle B has 53 gallons of gasoline and $1,929 worth of other goods consumption. The substitution effect, therefore, says reduce your gasoline consumption by 47 gallons and increase your other goods consumption by $129 worth. Since we've already calculated the final bundle C, we can now say that the wealth effect, the movement from B to C, tells us to consume 47 more gallons of gasoline and $2,071 more of other goods consumption. Notice that consumption of both gasoline and other goods increases as we move from the green compensated budget and bundle B to the final magenta budget and bundle C. Thus, both gasoline and other goods consumption are normal goods in this case, which is what we should expect given that we're using Cobb-Douglas tastes.